Can I have your attention for a few minutes before I hand over to Professor Hooft? Right. So it is a great pleasure to welcome today's distinguished speaker, Professor Gerard Hooft, a Dutch physicist, theoretical physicist, who is based in Utrecht, whose groundbreaking work has shaped the very foundations of modern particle physics. In 1971, while still a PhD student, Professor Hooft caused a sensation in the physics community by demonstrating that Yang-Mills gauge theories, which is the mathematical framework underlying the standard model of particle physics, could be renormalized. This pivotal result was presented in his doctoral thesis and immediately elevated the credibility of gauge theories as viable descriptions of nature. Indeed, without renormalization, gauge theories produce infinities, rendering them mathematically inconsistent and physically meaningless. A renormalizable theory, by contrast, allows precise, testable predictions essential for guiding experiments and uncovering new particles in particular. This mathematical consistency is what made the Bragg-Englert-Higgs mechanism not only plausible but also predictive, ultimately leading to the discovery of the Higgs boson in 2012. Such was the significance of Hooft's thesis that he was awarded the 1999 Nobel Prize in Physics together with his doctoral advisor, Martinus Veltman, for their work on the quantum structure of electroweak interactions. But Professor Hooft, his influence extends far beyond renormalization. He has made deep contributions to black hole physics and quantum gravity, including early formulation of the famous holographic principle, the idea that all the information contained within a volume of space can be encoded on its boundary. This insight has had profound implications for string theory and our understanding of the quantum structure of space-time. In recognition of his pioneering work, Professor Hooft has received prestigious honors, and many of them, including the Wolf Prize in 1981, the Spinoza Prize in 1995, and the Dirac Medal in 1999. He's also a foreign member of the UK Royal Society, among other many distinctions. It is particularly fitting that we welcome Professor Hooft as part of the annual Higgs lecture series, which is hosted by the Faculty of Natural, Mathematical and Engineering Sciences. This series celebrates the intellectual breakthroughs that underpin modern physics, and Hooft's work is inseparable from the theoretical framework that make the Bragg-Englert-Higgs boson a predictable and ultimately observable phenomenon. Executive Dean of Faculty, colleagues, students and friends, it is an honor to welcome Nobel Laureate Professor Gerard Hooft, who today will speak to us on the quantum black hole with almost no equations.
Thank you very much. I'm all under control now, and even the first couple of minutes of the talk which I'm going to give here has already been pronounced now, because I wanted to start with the work that ties my own research with that of Peter Higgs. I want to start with that to go over to discuss the black holes and the peculiar issues that have to be considered to understand how these objects behave. So, once upon a time, I believe that theoretical and experimental physics elementary particle physics as well as the science of condensed matter were practiced by experts with elegance and efficiency, with modesty and gentlemanly respect. I think Peter Higgs belonged to that generation of scientists who sometimes seem to be taken aback by all this homage when a particle that he had predicted indeed had shown up in the experimental observations. This is how I remember Peter Higgs. Let me go back to the 1950s. It was already in that time that it was understood that physics, that nature may well be rooted in symmetries. The question was, what kind of symmetries were they and how would this work? Well, there was a very ingenious paper by C.N. Young, now often called Frank Young, and Robert Mills in 1954. And they suggested to generalize the concept of electromagnetism. Electromagnetism is based on just one kind of photon, but you could replace that by 3 kinds of photons, and or a larger set of different particles, and follow the same principle, the same foundations of Maxwell's theory of electromagnetism. And that worked. It was, to my mind, the first result of attempts to reconcile quantum mechanics with special relativity. For a long time, people thought this was impossible because there were some abstract arguments about quantum mechanics saying that quantum mechanics seems to be in contradiction with special relativity. But that wasn't true, as Young and Mills showed very clearly. But Young and Mills then predicted that there would be more particles than the photon with mass 0 and spin 1. That was in conflict with what particle experiments had revealed. So only few people saw the importance of this idea. It was a nice abstract piece of work, but it didn't have any roots in the real world. That is how many people thought about this, but not my advisor. He was more impressed, and this was one of the few papers that we had to read as his students. Now I go a step forward to some 10 years or so, when Peter Higgs saw a way to give mass to all these massless photons. So there was something wrong with the massless photons. They were not observed in experiment. So we asked, can we make a theory with massive Young-Mills particles? And again, this was also a brilliant piece of work. But when he sent over his manuscript to the physics journal, there was a rather strong referee who said, well, this is all very nice, Mr. Higgs, but what does this have to do with the real world? Are there any ways in which you can experimentally check whether your crazy theory about masses makes any sense? And so Higgs got this letter back and he thought about it. Yes, there would be a way. Experimentalists would observe at least one new particle without spin and with mass. And Higgs described in beautiful detail how this particle would betray its existence. And it so happened that only Higgs came with this prediction. There were compatriots and, in England and also in Belgium, in Brussels, who had very much the same idea, but they didn't predict any new particle. They could easily have, because it was in the equation, so to speak. But they did not pay particularly attention to it. This particle could be difficult to observe, and so let's not focus too much on that. But now we all started to talk about the Higgs particle when slowly but surely the LHC, the big accelerator at CERN, was reaching the energies where most likely this Higgs particle could be found. And but this didn't mean that there were no problems. There were still problems, particularly in this more elaborate Higgs theory. Also Brauchel and Glare had models like that. The problem was infinities. When you try to calculate the effect of one particle on another particle, you are calculating how forces are transmitted between one another particle. But if you have many of these forces and these forces accumulate, you get a kind of backfiring of the equations, like a badly tuned microphone, and then soon the noises would start to become infinite. And those theories made no sense. So how do you make theories that can be used in physics and experiments, but they shouldn't predict anything infinite? That would be absurd. Nothing is infinite in this world. If there hadn't been any experiments that showed that we were on the right track, these crazy models would probably not have been taken seriously. But now they were. And look, sooner, only a few years after the first successes we had in theoretical investigations, the standard model of all particles was being formulated. Originally as just an example of the simplest possible solution of this genre for particles, for Young-Mills particles together with Higgs fields, but it could be rearranged in such a way that all particles known about in experiments actually had a place in that model. And the simplest of all those models was called the standard model. Then you could start to add things that nobody had seen and imagine what other things could happen. But the crazy phenomenon was that experimental physicists could only confirm everything that the standard model was saying, and did have no evidence for a long time of anything else than the standard model. But also for a long time the standard model itself was, experimentally speaking, not complete. The Higgs particle was the last particle to be experimentally observed, but that happened in 2012. And then it was quite clear that something very important had been found. So now we had not only models that agree with quantum mechanics, that agree with special relativity theory, but also agree with experiments. And this was a beautiful state for particle physics to be in, but also a bit disappointing because now there was nothing else to investigate anymore, or nothing else to check experimentally, because it all worked the way it was, it seemed. Well, experimentalists said, wait a minute, we can add a few more decimal places to our measurements. Maybe we'll find something that doesn't quite work. But every now and then, yes, they find 3-4 decimal sigma away from the prediction, but never something that is so very, very evidently in disregard with the standard model. So this is basically what I'm saying here, that now we have the equations for special relativity and quantum mechanics. Unfortunately, what these models did not include was the gravitational force. The gravitational force being the most basic force of all forces in this world. And yet the gravitational force was not properly taken into account by the standard model of elementary particles. Yes, you could say every particle feels gravity, yeah, but as soon as particles interact by way of the gravitational force, it was discovered that also in gravity there would be infinities, and this time this theory would definitely not be renormalizable, not the way that we had worked and been successful in studying the standard model. So we could either stop doing theoretical physics, or we could continue doing theoretical physics, but then we had to include the gravitational force as a next giant step in our understanding of nature. And of course, we had to do the experiments to see whether we are doing things correctly. Now that was a problem, the experiments, because to check gravitational effects in particle physics, you needed particles with energies billions and billions of times stronger than the particles that could be produced by the largest accelerator of CERN, the LHC. So how can we ever check that these black holes behave differently or the same way as other objects in nature? Are they just like stars and planets, or do they have some extravagant property that cannot be reproduced in any other object? Nobody could tell because we had no access to information. So this one important exercise had to be done. Check the behavior of black holes and such objects to investigate whether this behavior meets with the most severe demands that we can impose on the laws of nature that we do understand. The question is whether or not a modification of the known laws of physics can be made in such a way that we can predict and produce further evidence of the behavior of new objects in this world. For instance, in cosmology, black holes play a big role, but also in our theoretical understanding of the fundamental forces. Because it makes a difference whether black holes are ordinary objects or totally out of this world. Then we'll have to see how this can be understood in terms of all the interactions that we do know. And this seems to be a rather murky and dangerous terrain. But here, Stephen Hawking made a most remarkable discovery. He said, I can calculate something, and I can't say whether it can be checked by experiment, but I can say that this must be right, black holes must behave in this particular way. And his major discovery was that black holes will not only absorb anything that falls onto them, or that is being attracted to them, but black holes actually also emit particles. And what was more remarkable, Hawking could calculate how these particles will be emitted. And he said that's what he claimed. And this should in principle be experimentally observable. If we had accelerators 1 billion times as strong as the LHC, we would be able to check whether black holes really do behave this way. His calculation seemed to be impeccable. Yet I think there are difficulties. One of the obvious difficulties is that there's no experimental confirmation or disagreement or anything to be discussed, because we don't know how to do an experiment with such black holes. We've never seen them up close. And I can tell you it's a good thing that we never see them up close, because that would be extremely dangerous objects if you come in their neighborhood. So physics without experiments has, and this is a very well-known feature that we all know about the physical world. If you can't check some theory experimentally, odds are that it's completely wrong. And doing physics without doing experiments has, historically speaking, always been very wrong, unsuccessful. So how do we proceed? Which demands should we impose on a putative new kinds of laws of forces? And by lack of other branches of theoretical physics in this domain, the discussions on this issue intensified. But in my opinion, just as in the historical examples which I just told you about, investigators should look for more clues. Hawking did roughly the same thing as Einstein had done, but when I talk about Einstein, I really mean the young Einstein, the Einstein who looked like this. This guy in this patent office who was having some crazy ideas about the laws of theoretical physics. The old Einstein, you can also look pictures of him up in the web, but I'm not interested in what he did, because he made all the same errors as everybody else. So he wasn't as smart anymore as he was when he was young, because he has been within the time span of about 10 years. He designed two fundamental theories, special and general relativity. And besides that, also the science of atomic physics got big boosts from the observations that he had made. So he was a giant in theoretical physics in many respects. So yes, we can ask the question, imagine ourselves to be the young Einstein, the young one. How would he have reacted if he would have been confronted with this question? He would be very happy that his two pet theories worked so well, but he would also be annoyed that there would be no way to advance from there and understand better how quantum mechanics works. Einstein had big difficulties with quantum mechanics for very good reasons, I can tell you. And so it should be possible to do something better. But how would he then have tried to answer these very problematic questions? I think he would say, don't change the laws of physics, but just reformulate them. They are the same laws, but in a more general sense. And then you might be able to say something about circumstances that otherwise you had no access to. And of course, I talk about the speed of light. If mechanical objects reach speeds, velocities, comparable to the velocity of light, then strange things happen. And that was what he was good at in formulating or reformulating. Now he would definitely try to do the same thing with a new situation. Try to modify the laws of nature such that whatever comes out about the kind of information about black holes should be testable and should be indicative of how the laws will work. So yes, try to do that. Now, soon after Einstein had finished his second major theory of general relativity, there was a well-known astronomer by the name of Carl Schwarzschild. Schwarzschild derived the first non-trivial solution of Einstein's equation. He said, Mr. Einstein, in your publication of 1915 in the Academy of Science, you have written down these beautiful equations. But what you haven't done is write down the first solutions you can write down. I can solve this equation, certainly in the case of spherical symmetry. This is something that an astronomer had to notice. If you have equations and you have a spherically symmetric object that obeys these equations, it's rather easy to solve the equations. Because in case of spherical symmetry, you basically only one independent variable, the distance from the origin. And then your equations become one-dimensional. And many good mathematicians and scientists can solve practically all spherically symmetric equations. So, yes, he could do that. He wrote it down and sent the solution to Einstein. And he asked Einstein, what do you think? Because I see there's a strange kind of problem in my solution. But that was very strange because the problem that he saw could not be attributed to the equations. Einstein's equations are probably derived in a correct manner. So how could he ever have arrived at something that is so strange as a black hole? Because what he found is that if two objects with large masses come close to each other such that the distance between two objects is smaller than the mass in natural units, then these particles will attract each other with velocities faster than the speed of light. And that's also what comes out of the equations. Or it looks like faster than the speed of light. Something is very wrong about this. So what do you think? And Einstein said, well, I think your solution is wrong. There are no such things. But actually, of course, now we know that there are such things as black holes. They have been confirmed experimentally. So there's nothing wrong with this idea. But yes, these black holes are very strange objects. So how can we understand what happens when a black hole attracts something and whatever it is that it attracts is going through a magic line, a border, like the Eurozone and the British pound. I mean, if you cross that line, then something changes. And the units are also changing. So how do I deal with that? And the problem was that there would be infinities again. Well, as a physicist, I heard about infinities before, so I know what to do if that happens, I think. But in this case, it was unclear what to do. And in particular, the observation was if you have a black hole, and the black hole has a horizon. I promised I wouldn't write down equations in this talk, so you must accept the idea that there's a magic sphere surrounding the black hole, which you call horizon. If you try to go through that for a short moment, you get infinite energies. Infinite energy, how can that be? The whole black hole doesn't carry infinite energies. Yes, I mean for a local observer. A local observer might say that these particles get infinite energies. But the local observer himself is also not clean about this. So he also would be carrying absurd amounts of energies. So something very strange happens at the horizon of a black hole. So Schwarzschild said, whatever I'm saying, something is wrong, and I don't like that. What do you think? But it turned out that you can answer those questions, but the questions are very paradoxical, the answers are very non-trivial, but extremely interesting. And I believe if we now search for those answers, and you get all the answers correct all together, then we'll learn something about these forces, and we will learn how to deal with the problem of reconciling the electroweak forces, the strong forces, and gravity. All that should be in one grand scheme. There shouldn't be different theories for different forces. There should be one theory for all forces. And the belief is that that will happen if we manage to solve this problem. So the problem was really very interesting, a very interesting one. And it was like a jigsaw puzzle. Well, we scientists are used to solving this jigsaw puzzles. I like them, so every now and then my table is full of 1,000 pieces of jigsaw puzzles. So yes, but this jigsaw puzzle became too complex for us to solve. And now here, with one eye onto the historical facts, history always tells us, don't give up. The answer is there, but you have to look more carefully. So yes, we learned how to look more carefully. And one of the experiences is that we need precision and accuracy. I mean, logical precision. So the logical arguments that you're using must be perfect, and the calculations must be as accurate as possible. And then you may be able to learn something new about these crazy forces, the way they act together. So like the young Einstein, we're going to use all the known laws to see if you can understand how black holes behave. And there's one thing that I would say you should not do. What you should not do is throw away everything you have and replace the laws of physics by new laws of physics. You often hear people say that. We are going to change the laws of the horizon because that's the new physics, because then maybe the infinities will go away. But that's not what's happening. If you make changes of the way people have proposed, you'll make the problems worse. In general, if you just pull the equations out of your hat, you pull the wrong equations and you're not getting anything better. So use the equations you got, but apply them under unconventional circumstances. And that works a lot better. I claim it even works so well that we can say that some of the preliminary results, including the results of Stephen Hawking, might well be up to be corrigible. So that's not, those solutions are not quite right. And I'll try to explain to you why I think that even Stephen Hawking did not quite come with the correct solution. He did, however, shed light on the quantum mechanical effects. So a black hole is normally considered a classical thing because it's much, much bigger than a scale where you see quantum mechanical effects. But we can imagine black holes to be as small as we like because, for instance, Carl Schwarzschild did not say how heavy his black hole is. It could be very, very light, very, very small. And then it could be so small and so light that you might expect that this should be something where the new physics, whatever it is, should play a role. But let's try to use only the laws that we know about as well as possible. Now, this discussion, of course, is not over, far from it. In this lecture, I show that there's actually a very strange singularity near the black hole horizon, and I claim that that's going to be indicating what's going to happen there. And that singularity will play a crucial role, but we don't yet know for sure. This is just a theory. But and another thing to consider is that Hawking predicted the intensity of the radiation of a black hole. The black hole emits particles. How many particles per second, and what is the nature of this radiation coming from a black hole? Well, what they found was the radiation is thermal. It is just like a light bulb being heated up to a certain temperature. It will emit that kind of light. So it's thermal light that the black hole will emit and nothing else. But then Hawking said something very remarkable. He said it's going to be perfect thermal radiation. There's not going to be any detectable deviation from pure thermal radiation. Well, in an abstract sense, this may be true, but I believe that if you look very carefully, you will find fluctuations, and those fluctuations cannot be completely thermal. There will be deviations from that, but that's going to be a very difficult problem to deal with. And furthermore, I gave myself the task to leave the equations out, and that makes it another little bit harder to explain how it goes on. So, but when you look at black holes, there's one fundamental difficulty that comes about. That is, particles go into the black hole. But what about particles going out? Well, Hawking gave the equations of how many particles come out, but he didn't give any further details. He said there are no details. What do you mean there are no details? Of course, there must be details in these particles. But if I compare a black hole with a star, or with a brick, or with a molecule, or anything else, all these objects have properties that explain to them in what state they are, and that help us describe how the particle will behave, whether the particle will emit another particle or absorb another particle. All that should be given by equations. How do we understand those equations if the outgoing particles are not allowed to have any structure? And in particular, something must happen when they go through the horizon. Well, when I asked this to Hawking, he did not agree, and that this became an eternal discussion. It's very sad that we cannot continue this discussion now, because now I have further arguments to believe why I think I'm correct. But and that is that a black hole is not a perfect sink of information, but it's not like an impeccable washing and drying machine that doesn't make any tears in your clothes or doesn't leave any dirty water behind. No, it's more complicated than that. The gravitational force has another nasty property. What we have seen about the standard model of particles was that these forces become infinite. So in the standard model, the infinities eventually cancel out. But for a particle going through the horizon, that was very difficult to imagine. Something was not quite right. And the reason is that gravity is not a renormalizable force by itself. This much we can prove. Or if you want to have a gravity without infinities, you have to change something in a way that actually nobody wants. You want to describe the non-perturbative domain of gravity as being, not really described by laws of physics that we know them. So there's something wrong in this whole picture. If particles hit the horizon of a black hole, the standard model forces will always be too weak to transmit information from the ingoing particles to the outgoing particles. Because this is, I think I had it on the previous slide also, there was a question, if a black hole absorbs an object and a few minutes later it emits an object, does the emitted object have any memory of what went in? So do the outgoing particles have any memory, any link to the particles that went in? And Hawking said no, and I say yes, it should have. But something else has been found, and that is in the ordinary standard laws. You know, general relativity is now considered to be a theory that is understood by most of the scientists. But there was another conclusion that could be computed, and that was done by Mr. Shapiro. I just want to show the next slide first. Shapiro calculated that if you have a ray of light being emitted by a distant star, and this thing in the center, suppose that this is the sun, and this is a light ray coming from a distant star, reaching here, the Earth, and an astronomer is measuring the position of the stars. Well, because the light is being attracted by the sun, the light doesn't seem to come from the direction where the star is. The star is here, but the light seems to come from a point somewhere out here. And this angle can be computed. And this is what Shapiro did. This is the Shapiro angle. And this was a way actually general relativity could be first confirmed by experiment. To notice that stars that you see just very close behind the sun, you see the light almost grazing by the sun. You see that light's being deflected. And the deflection could be measured, and it was found that it agrees with prediction. But you wouldn't say that this force is infinite. It looks like a very calculable force, and all the details should be understood. Yet, in a way, this is the force that does become infinite if the starlight would actually touch the sun, and not only at the border of the sun, but at the horizon. If the sun were a black hole and the particle would come to the horizon, then this angle would become very big. Not only that, there is another way in which I'm going to use this force. I'm going to use this force in order to find how to use less conventional laws of nature to understand how information can go from behind the horizon to our place. And how do we do the physics of that? So I have to explain without equations doing that. That's not so easy. But it was found that we could compute this, and the answer could be used in the following scenario. Instead of the sun, we take the same phenomenon, but we're not using the sun as a deflector of light, but we use just another particle. Because just a minute ago I said that one of these particles will carry almost infinite energy. So this red particle and this green particle, they carry infinite energy. The energy, but even if the energy is very large, then it will do something that's not infinite, but calculable. It will take the light of the other particles which go by, and if they come very close to this particle, the light is being dragged along. So this is a drag effect. The light of the other distant particle will continue there. This is what you would see if you would be in the coordinate frame of this light particle. But you could also go to the coordinate frame of the green particle. Then you see that the green particle is being dragged along by this red particle. This drag effect is the same physical phenomenon, just under slightly different circumstances, as the Shapiro delay. It's a Shapiro delay, but also a Shapiro angle. Yes, the particles also delayed a little bit by the Shapiro effect. All that is taken into account by just having a small vector that this particle is being dragged along. Most other scientists do not take this effect into account, but for me it is crucial. It's crucial to understand why the black hole behaves the way it should. So let me continue with that. Now, it's all very nice to continue with that, but there is a surprise waiting for us, another surprise. If you try to apply this phenomenon in a black hole, you'll find, and if you'll find that you can look at a solution which describes in this white quadrangle, this is a shorthand notation of the entire universe surrounding a black hole. So the entire universe of the black hole is this white quadrangle. But now the mathematicians discover you can open this up. And when you open it up, you find that there's another universe here. It looks exactly like this one, and in fact it has actually exactly the same characteristics as this one. But there's another universe, and it's glued together in a very snugly way to another universe. So you don't only have to deal with one universe, you are dealing with two universes. And the two universes have things going in. If time runs, in this quadrangle, time runs from here to here, so time runs in a vertical direction, or close to, as long as it stays inside this light cone, it can also go under some angle. And under some angle, the light will be absorbed by this horizon. At this point here, there's some infinities taking place that we don't quite understand, at least not yet. But you can apply now the Shapiro effect to these particles, and it has an effect on the outgoing particles. These are particles which, here in this picture, they're very far away from each other, but if I look at the particle which went in longer ago, and the particle which goes out later, then they all go and sit very close together at the center. And at that point now, you can say that this Shapiro effect is going to become infinite. It's going to become infinite if, let me first consider these remarks before I forget them, that these two universes are connected here in a very strange way. The strange way in which they are connected is that if time runs here from down to up, the time runs here from up to down. So in fact, time here goes in the other direction as here. It goes back to the past. That looks very strange because you would think the time runs the same way everywhere. Yes, but when you approach this point from the right here, then the closer you come to this point, the slower times go. And at this point, you're on the horizon, time doesn't go at all. If you pass this point, time goes in the other direction. So this is a very strange universe. It has the time direction is wrong. And how can these two possibly be connected together? Well, mathematicians know how to understand that. And they now say that space and time in the black hole is divided into 4 regions, 1, 2, 3, and 4. The blue regions are not so important for my argument. I only want to get to the blue regions for a very small distance. I don't have to go very far. So the blue regions are of no significance. I had a question about that yesterday, an interesting question, that there's a singularity here in the blue region. How do I handle that? I don't handle it. I don't have to be worried about this singularity. It doesn't play a role in the calculations. So that was that answer. But it's very strange to have such a world. And now again, we want to say if you have a particle going in, it should be affected, or a particle going out should be affected by the particle going in. And the remarkable thing is that we use, the mathematical trick that I'll talk about here is that that the universe here has a phantom universe sitting at the other side. And so now we are going to study, by putting a magnifying glass here, we see that the basic interactions take place here. But the Shapiro delay now could drag particles along in the opposite direction. So a particle coming from the past here to get out and be observable as a physical particle, if the other particle comes from the other side, it might drag this animal along. It might drag the other particle along to get across this horizon here, which is magnified in the magnifying glass, so it's a small effect. And that small effect makes that the particle no longer will appear, but will disappear into this singular region in this domain. So a particle can disappear by the Shapiro effect. A particle can also appear by the Shapiro effect if I send in something with negative energy. How do I send in something with negative energy? Oh, that is easy in quantum physics. We say we annihilate the particle. We give a state, you have particles in that state, we have in and outgoing particles there, we just remove an ingoing particle, and that removal does the opposite of adding an object, something to the particle. No, we remove it, and therefore the drag effect goes in the other direction. So a particle which was planning to be ignored by falling into this singular region, that particle could be pulled out of the horizon by absorbing a particle among this array of ingoing things. So I imagine that most of the people here who listen might not be able to have a direct picture of what I'm talking about, because it's very subtle, these things. So what I want to talk about is the fact that there's all these remarkable questions to be answered one by one if you want to study a black hole. And if you solve them one by one, you'll discover that the whole thing starts to make sense. And that is my most basic argument which I want to defend here, that if you just look at what I'm saying now, you might not understand what I'm saying. But if you follow in a more abstract way what I'm saying, you see that there are all these problems connected to black holes. One of the problems is this strange phantom universe which sits at the other side is one of the problems. The Shapiro effect, which you didn't realize could be so important, is very important in this domain. And well, there are a number of other issues which I still haven't mentioned yet, which are also going to play an important role. So the point about using the Shapiro effect is this. Let me first. I have this. This is the drag effect. So here goes a particle into one point of the black hole. The outgoing particle is being dragged along and carried across the horizon by this effect. So this is a very important effect. And here you see in the opposite direction that can also happen. So now we want to take this into account. And for that you need mathematics, you need the equations, you solve the equations and see how this happens. And then you learn something very remarkable. And the remarkable thing is that the position of an outgoing particle is being affected by the momentum of the ingoing particle. So the ingoing particle has a very large momentum. Certainly on the horizon, certainly as in regard with the other particle, its momentum is gigantic. So it has a big drag effect. That's the Shapiro effect. So, but the other things that should somehow resonate in your mind, what I'm saying now, is that I'm talking about position and I'm talking about momentum. The momentum of the ingoing particle determines the position of the outgoing particle. And this relation between momentum and position you must have heard of before. We have in quantum mechanics, the position of a particle is not independent of its momentum, but it's related in a remarkable way. And that is that you have particles in quantum mechanics that are actually forming waves or wave amplitudes. And in quantum mechanics, we've learned to say that if you want to know the position of a particle, but you only know its momentum, you have to take the wave function in momentum space, Fourier transform that, and then you get a wave function in position space. So the mathematical procedure of Fourier transformation, if you know what it is very important in this whole story. So the rule that you discover, that you get by paying nothing, you didn't need any new law of physics at all, you only needed visible effects, the Shapiro effect in particular, to be able to say that the outgoing particle is determined by the Fourier transform of the wave function of the ingoing particle. And those then give you an answer. They say the outgoing particle does depend on the ingoing particle. Now I can compute it. And I don't only need vague concepts that many physicists introduce to avoid the information problem. No, I solve the information problem this way. At least almost, but not quite. I have not yet, whatever I've said so far has not been totally sufficient to solve the information problem. Where's the information ingoing particle going? Suppose the ingoing particle sends the outgoing particle back into the universe, into the forbidden region. Where does its information going? I haven't said that. I haven't said that. But that is because I haven't yet said how to deal with that in this picture. You see, a Fourier transform can be done if you look at the wave function that ranges all the way from minus infinity to plus infinity. Now on this line, the wave function goes all the way from here to there. On this line, it goes all the way from here to there. That means that the wave function of our universe is going to conspire with the wave function from this other universe in order to get the complete wave function on this line. And the same thing about this wave function. And now here, this wave function from minus infinity to plus infinity should be the Fourier transform of this wave function. So those of you who have learned what the Fourier transformation is will appreciate the remark. The very good mathematicians will put a big question mark here. The question mark is, yes, you said so, and you use both universes to go from in to out. But if I can only see these particles on this one half universe, I don't have all the information I need to compute the outgoing particles. So there's still something wrong in the argument. And so yes, this is why I had to show this whole picture first, before explaining to you that the Shapiro delay helps you to find the information of the outgoing particles by you doing this mathematical transformation called Fourier transformation to get there. So there's still something not right in that thing, because I have a universe which contains two disjoint sub-universes, so to speak. But the other thing is, where does a sub-universe come from? Is that another universe? What is it? Where is it in our universe? And having big disputes, where should you find this other universe? And in particular, Hawking had all wild ideas. He was imagining that in this universe it was Brigitte Bardot, and in this universe was Hawking. And he goes in there, and out he comes with Brigitte Bardot on his lap. That was one of his favorite toy ideas that he would attach to this picture. But that would only work if this universe and this universe would be totally different. Now I'm going to say, no, they can't be totally different. They have to be identical. This one is identical to that one. And then, if you say that, then this whole picture changes. Because if you say that this is identical to that, then also the ingoing particles here are the same particles as the ingoing particles here. Their wave functions are also identical. And this is something that you never hear quantum scientists say, that the wave functions are identical. Because wave functions are never identical in the quantum experiments that people think about. Well, here they are, and the wave function here is identical to the wave function here. But also on this end, this region of the universe here is the same as this region of the universe there. So also here the wave function is identical. And now again you can ask, what about this Fourier transformation? The Fourier transformation also does things which are identical in one sector of the space and the other sector of the space. So also the Fourier transform does this right. And now, okay, you have to do mathematics to see how to formulate the boundary conditions. And this is a subtle calculation that you have to check. And I had arguments about that with my colleagues in this field, because they said you're doing something wrong. And I said, no, you have to choose your boundary conditions better. And then it all comes out it works. So my claim is, if you do this right, if you look at the boundary conditions and you look at the wave functions, then everything comes on its feet. What's more important is that now there's no information anywhere that you cannot reach. So there's information here, there's information here, and all these are connected by either the Shapiro effect or by the statement that this universe is just a mirror image of this universe. And then all these arguments together tell you exactly how the outgoing particles react on the ingoing particles. And my claim is this now solves the information problem. And now that is already stated on these remarks. So the discovery that you make this way is that one universe is the mirror image of another universe. You can even see yourself in that mirror. But don't be upset about what you see, because you will see yourself going backwards in time. Now, what does that mean? How can you ever have a mirror where you see the other guy going backwards in time? Well, sorry, I lied to you. You don't see yourself going backwards in time, because to see that, you have to go faster than the speed of light. And sorry, you can't go faster than the speed of light. So the signal is too slow. The signal is so slow that you can't see yourself going backwards in time. You only see yourself before time equals minus infinity or beyond time equals plus infinity. That's kind of images that you can get, but you don't mean a thing anymore, because by that time you don't exist anymore. So again, if you look, you get problems, you get mysteries, you get question marks, and you get remarks from your colleagues. But then if you look carefully at all the boundary conditions, all the mathematics, you put it all together and you solve them one by one, you see it all works out. So this actually solves the information problem. But solving the information problem, so when you do all this, I explained here in my slide that for some it is a diabolical nightmare that if you can't find the proper boundary conditions. For some it's a mathematical riddle, but for me it's a bit of sunshine. It's so beautiful that these things, if you do them correctly, they seem to work perfectly, and the ingoing information now does return to the outgoing radiation. Now I realize that with this kind of mathematics, the black hole is not fundamentally different from a brick, or from a fundamental particle, a molecule, or a star, or a galaxy. It has all the same characteristics. The information of things going in will be returned to the information of the things going out. And well, Stephen Hawking, according to Stephen Hawking, this other universe was another universe inhabited by different people than the universe that he lives in. And also Kip Thorne says the same thing. I don't know whether you remember the movie Interstellar. Kip Thorne has been an advisor for the script of the Interstellar. But according to Kip Thorne also, if you go through a wormhole, through a black hole, you can emerge somewhere else and you are in another universe. He forgot to say that you are entering into another universe, time reverses. So you're going backwards in time in another universe, which is very unpleasant for most travelers to go backwards in time. So that you can't have. And so the situation is different from what most scientists will tell you. Now there's another little remark, that is that the angular momentum of the outgoing particles are always fixed. It is much easier to do the calculation with a particle being in a fixed angular momentum state than in a fixed position around the horizon. Because angular momentum is conserved, and so once it has a certain angular momentum, it keeps that angular momentum forever in its behavior. And that means that if you establish angular momentum values of L and M, then you get only a one-dimensional equation. So you can actually solve the mathematical equations in angular momentum space very easily. And you find a remarkable thing, that if you fix the angular momentum, there's exactly one particle that can enter into the black hole. That one particle will be undergoing this Fourier transformation, and one particle comes out of the black hole at the same spot. That's very convenient because it helps you solve many riddles about black holes this way. But it also generates new problems. So I'm not saying that I've solved everything, but the equations that are here, most scientists be puzzled about and try to solve. I say, no, those equations I can solve, but there's still many other equations that are a mystery for me. This is a little demonstration. I have made here these two universes. I hope you can recognize them. These are the two universes, and this sheet is the two universes only for one value of its angular momentum, or for one point on the sphere around the black hole. So the sphere is not given, just the two regions, region 1 and region 2. And then the claim is that this region 1 is equal to this region 2. So actually what you should do is you should fold space and time up. So I fold up, and I do this in such a way that at the tip I made a rotation of 180 degrees. And then this makes the same rotation, and I get this structure here that really my universe looks like this. The particles in region 1 are identical to the particles of region 2. So I have 1 and 2 sitting opposite to each other. But if you have a particle on the region 2, that the same particle sits at this side as well. So this is the proper way to describe the space-like components of the or the radial components of the black hole. And in this way, you see that there's no region with forbidden information that you can't mention. Yeah, there's a problem in the regions 3 and 4, but those are not playing any role. You just do all your physics in region 1 only. But there's one problem with this. So I took this piece of paper to fold my universe, because I don't know whether you see there's an exceptional point in this picture. The exceptional point is this. This is the point around which I made a rotation of 180 degrees. But you see it's singular. This point is what we call a conical singularity. So I forgot to say anything about the conical singularity. No, I didn't really forget. I just rescued it in time. So at this point is a conical singularity. How do we handle that? And this is a valid question, but it's easy to answer. It is a conical singularity, but it's a very mild one, because I can smoothen it out. I can just take scissors and cut a very little piece out and glue the ends together, this becomes a smooth, somewhat singular, but not really singular point. This means that there's matter at this point. Matter controlled only by the trace of the Riemann tensor. But so at this point there's still matter, but everywhere else there's no matter around. And that's good because at every point, angular momentum point, only one particle goes in during the lifetime of the black hole, and then the particle comes out again. So, so there is indeed very little matter on all the other points of the black hole, except here, this is a conical singularity. That conical singularity actually is a sheet, because I neglected the angular variables. If I put the angular variables back in, this becomes a sphere with the radius of the horizon. So that sphere is actually a string. It's a string world sheet, but an unconventional string world sheet, because string theories normally put their world sheets in a space-time direction. This is a world sheet in a space-space direction, so a Euclidean string. But I say, wait a minute, to go from Minkowskian strings to Euclidean strings is very easy mathematically. So if string theorists know how to deal with the Minkowskian strings, I think they'll tell me what to do here with this kind of string singularity. And so here I find a connection between the kind of physics that I've been using and string theory. String theory may be telling us how to deal with this situation here. I haven't come that far, this is still a mystery, but I'll leave my string theory colleagues to consider how to handle this point. And that will hopefully bring me in contact with other approaches to black holes, string theories about gravity, and so on. So by arguing this way, I hope to have convinced you, although you didn't see the equations, I hope I have convinced you that this makes a lot of sense, and if you put everything together, you may get a good theory for black holes, including the way they handle information, and eventually you'll see how everything behaves. So this picture I want to use as my last picture. It shows the brownish regions, which are the original solution that was written down by Schwarzschild, which only has one point for every point in the universe, labeled by the coordinates r and t. But then if you fold this open, you get the orange and the pink and the purple and the orange and the pink sheets. These are here you have x and y, here you have minus x and minus y, which describes the same universe. So all these are carbon copies of each other. So every single particle has only one spot in the RT space, is one spot in the XY space, and also one spot in the minus x minus y space. So this is how you have to understand how things behave. I think, yes, I should stop this, because otherwise I can go and talk forever. It's better to try to continue with discussions. If there are questions or remarks or criticism, whatever you want to come with, I would like to hear. So thank you very much. And